Okay, so with some acid-base reactions, it turns out a single reaction can't tell the entire story of what's happening, or rather, some reactions happen in a series of steps, and it's easier to describe those steps with multiple reactions than it is with one big one. So let's have a look at what that might mean. Oxalic acid is like two carboxyl groups back to back. It's it's Huku, like that. This COOH is a carboxyl group with an acid attached to it, or a carboxylic acid, and this is COOH going the other direction, so that's another carboxyl group. And they say we're adding hydroxide to this. So when you first do this, one of the hydrogens will come off this acid, and that will give us HOOCCOO. This is hydrogen oxalate. And the hydrogen that came off will combine with the hydroxide and give us water. This is the first reaction that happens with oxalic acid. If you have 1,000 oxalic acids and you start dripping in OH one at a time, one by one, those oxalic acids will each give up their first hydrogen. None of them will give up a second hydrogen until they've all done this. They'll keep it as fair as they can. Say, okay, everyone give up one hydrogen. We'll neutralize the OH that way. But eventually, after 1,000 OHs have been added, all of the oxalic acids will have turned into hydrogen oxalate. And then, if you keep dripping in OH, something else has to happen. At this point, if you keep adding hydroxide, then these guys go, okay, well, has everyone given up one hydrogen? Yeah, we all have. We're all down to we've all gone from two hydrogens down to just one. Well, now to keep neutralizing base, we have to start giving up our second hydrogen, this one. And so now hydrogen oxalates will start dropping down to just oxalate ion. And this hydrogen coming off will give us yet more water. And so that's your second reaction. This is called a stepwise reaction, and this is the first step, and this is the second step, or you can call this the first reaction and the second reaction. If you wanted to, I prefer to write them this way because I think it contains more information and it's fairly easy to follow, but an option that you have once you've written two reactions like this is you can add them together. You add up the left sides and you add up the right sides, and then you clean up spectators. And what that gives you is an oxalic acid, CCOOH, and a hydrogen oxalate, OOCCOO minus, and two hydroxides, and on this side we get a hydrogen oxalate, and an oxalate, and two waters. And you may have noticed there's a little bit of duplication in here. We have a hydrogen oxalate on each side. That doesn't need to be there. If we throw that out, what's left is like an overall reaction, which says if you take an oxalic acid and you add two hydroxides to it, it will get stripped all the way down to an oxalate ion, and you'll end up with two waters. So this is a summary of the above two reactions. So they say here they want two quantitative reactions, and so I believe this is the answer they're looking for. This is a nice way of condensing it, and you will see that sometimes. If you see a reaction like this and you see two OHs, you should think this is actually two different reactions, and you could write those if you needed to, starting with this and in two steps getting down to this, because this is your acid, and this is like two steps away, the conjugate base. This is what it looks like after it's lost two hydrogens. Okay, let's try that again many more times and make sure we got it. Okay, a spill of battery acid, which is sulfuric acid, is H2SO4. You can see this has two hydrogens on it, so you probably have an idea what's coming. We add sodium hydroxide to this. Sodium hydroxide solution contains sodium ions, which we don't care about because they aren't acid or base, and hydroxide, that's the good part. So if you take sulfuric acid and add hydroxide to it, the first thing that will happen is one hydrogen will come off and take us down to hydrogen sulfate ion. Oops, sorry, I started to write 2 minus, which is quite wrong. It's just HSO4 minus. And the hydrogen that came off combines with the hydroxide, we get a water. So if you mix equal amounts of sulfuric acid and hydroxide, you will get a whole bunch of hydrogen sulfide. If, after you've done that, you keep adding base, now the second hydrogens will start to come off and you will start getting just sulfate ions and yet more water. Easy enough? I won't do the summaries anymore. They're pretty easy, and I don't think they're necessary here. They seem to want to see these separate reactions to show that we know how to do that. So this is, we have acid, we pour hydroxide on it, eventually it all turns into this, then we keep pouring base on it until it all turns into sulfate. At this point, there's no more reaction that could happen, and if you kept pouring hydroxide on this, I don't believe you'd get any more reaction. You just have a puddle of hydroxide accumulating on your sulfate, but this can't give any more hydrogen. It doesn't have any more, so that would be the end of the chemistry. You'd just be diluting the mixture at that point. Okay, potassium hydroxide, which means potassium we don't care about, and hydroxide, which is a base, added to phosphoric acid. H3PO4 plus OH minus. And they say 2 quantitative reactions. This can do 3. I guess they only want the first 2. I'll do all 3 just for grins, but I guess they only want the first 2 reactions here. Because this can give away 3 hydrogens, the first thing that happens is it gives a hydrogen to the hydroxide, because this is by far the strongest acid in this list, so it will give away hydrogen to the other thing. That gets us dihydrogen phosphate ion and some water. After that, if you continue adding hydroxide, this will give away a second hydrogen. You'll get HPO4 minus. And the water keeps on coming. Apparently this is all they want, but I'll write the obvious just in case you'd like to see it. If we have hydrogen phosphate and we continue dumping hydroxide on that, this will give up its last hydrogen, become the phosphate ion, and we will get yet more water. Okay. Barium hydroxide. Now, barium has valence 2, so this is actually BaOH2, meaning it contains 2 hydroxides per molecule, but that's not going to change what we write for our reactions. We're still going to do these 1 hydroxide at a time. It's just, if you're using barium hydroxide, you'll only need half as much of it as you might think, because every molecule, or every unit of barium hydroxide contains 2 OHs. But that's not going to change what we write for our reactions here. Sulfurous acid is H2SO3, comes from hydrogen sulfite. And if that encounters hydroxide, this will give away a hydrogen and become HSO3 minus, and we'll get some water. Then, if we have the hydrogen sulfite and we continue dumping hydroxide on it, it'll give away its second hydrogen, become the sulfite ion, and yes, you guessed it, more water. Lithium hydroxide means lithium, don't care, and OHs. And citric acid, I am going to have to look up. I have a general idea what it looks like, but I'm not nearly good enough to do the formula. C3H5O and then 3 carboxyl groups. C3H5O C3H5O. Now, you know what a carboxyl group is. This is what we have in formic acid and ethanoic acid, vinegar, all kinds of things end with a COOH, and this H is what makes it an acid or a carboxylic acid. Citric acid is like that, except it happens to have 3 of these on it. So when it starts off, it's got 3 COOHs, each of them able to release a hydrogen. And then we're going to dump OH on that. So when that happens, this is a little tedious to write. One of these carboxyl groups is going to give up its hydrogen, while the other 2 do not. So in your first step, you have C3H5O. That part's never going to change. Then we have COOH2, because 2 of these have yet to give up their hydrogen. And then we have another COO, which has given up its hydrogen. So here we have 3 of them with hydrogens. Now we're down to 2 of them that have hydrogens and 1 that doesn't anymore. And let us not forget, we get water off of that. So that's our first step. Second step, C3H5O, COOH, 2COO. If we keep adding hydroxide, now another one of these has to give away its hydrogen. We're going to be down to 1 COOH, and we'll have 2 of these stripped ones that are a carboxyl group with no hydrogen. So C3H5O is always there. And then, I guess I don't need brackets on this. If there's only one of them, I can just say COOH. Actually, I think I will still bracket it. I'm not positive these brackets are necessary, but I think they make it read nicer. And I confess I don't know the rule for doing these, so I'm just trying to make it look as clear as I can, which is kind of a rule too. No notation is good if people can't understand it, so making it clear is definitely a thing. Okay, so we went from 2 of these have hydrogens, 1 does not, to now 1 of these has a hydrogen, the other 2 do not. And now we have to do one more step where this thing gets hit by a final hydroxide. So C3H5O, COOH. Okay, so if this loses 1 more hydrogen, then this last COOH turns into a COO. So we're going to have C3H5O, no change to that part, and then COO 3 times, and that produces 1 last water. You probably noticed I kind of blip back and forth between writing this HOH and writing it H2O. They're completely equivalent. Sometimes I find this makes it easier to read a reaction, especially if you're trying to identify like a base and its conjugate acid. In other cases where I'm not paying as much attention to that, I will slip back into writing H2O. So this can be helpful, but it's never really mandatory. And if you write this instead, no problem. Okay, I think that does it for citric acid. What else have they got? In chemical analysis, hydrochloric acid is continuously added to a solution of sodium phosphate. So when sodium phosphate dissolves, we get sodium ions. Don't care, because sodium isn't acidic or basic. So phosphate is the interesting part of that compound. And to that we are adding hydrochloric acid. Now, I'm not going to write HCl because when you put hydrochloric acid in water, in the blink of an eye, it turns into hydronium ions. And also chloride ions, which I don't care about for the same reason as these. Chloride ions are one of the worst bases ever. They never do anything interesting. They almost never do anything interesting. So these are the interesting players. We have a phosphate that's prepared to take some hydrogen, and we have hydronium ion, which is more than happy to give away hydrogen. So what can happen? This will take 1 hydrogen, HPO4, charge comes up to 2 minus, and that H3O is now just water. If we keep adding H3O, we can get a second reaction to occur. This is now H2PO4. I've been thinking about those arrows that I just used, and I'm going to change those in a moment, but let me write these reactions and then we'll discuss it. We could keep going and do one more reaction, and I'm going to write that and then I'll explain why they talk about two quantitative reactions. If we have H2PO4 minus, and we add one more H3O to it, we get H3PO4 and H2O. Now, this first reaction, they're saying these first two reactions are quantitative because this is a very strong base, and this is also a very strong base. So if you compare the strength of the acids in this reaction, the strongest acid on this side is H3O. The strongest acid on this side is hydrogen phosphate, and the difference between them is very, very large. So I wrote these arrows kind of out of habit. What I should have written here is just a straight arrow to the right. This reaction will happen pretty much to 100%. This second reaction, same thing. Because H3O is much, much, much stronger than the dihydrogen phosphate ion. So you can expect this reaction to have an equilibrium that is very far to the right. However, things get at least a little bit competitive when you find phosphoric acid, whose K is only 10 to the minus 3, or 6.9 times 10 to the minus 3. H3O is a very strong acid, but this is no slouch. We cannot say that this reaction will go 100% to the right. This reaction actually has a meaningful equilibrium to it, where some of the H3PO4 will dissociate and some will not. So here is a more reasonable place to write an equilibrium symbol. So this reaction is definitely going to happen, and this one will happen partially. We could figure out how much if we wanted by doing our H3O equals root Ka times acid concentration. We could do a number crunch and figure out how much acid is dissolved here, but it would not be 100%. It may not even be all that close to 100%. So when they say two quantitative reactions, they're saying show us the two reactions that are definitely going to go to completion, and that would be these two. I put in this last reaction just because more practice is good, but it's fair to say this isn't quantitative because the difference in strength between these two acids is not overwhelming. It's only a factor of a little less than 1,000. Fair enough, I hope. Write the complete chemical equation describing each step of the continuous addition of nitric acid. Now, nitric acid is HNO3 aqueous, but when you put it in water, what happens? After a moment, you're not going to find any nitric acid because instead you will find this. So a solution that we label as HNO3 is technically a solution of H3O, which is really strong acid, and nitrates, which we don't care about because they're a really terrible base. So H3O is the big takeaway from nitric acid. And we're adding it to sodium oxalate, which is OOCCOO2-. This again is a carboxyl group, COO, and then this is a carboxyl group. It's two of them standing back to back, so they're pointing in opposite directions, but either way, there could be a hydrogen right here, and there's going to be in a minute, and there could be a hydrogen over on this end, and that will happen also. Because when this meets H3O, the reaction here is Hello, I'm an acid. Would you like a hydrogen? Why, yes, I would love a hydrogen. So we get HOOCCOO and water. So this is the oxalate is a base, and here's its conjugate acid. It's gained one hydrogen. Here's the acid and its conjugate base. And they're saying this is a quantitative reaction, which would mean arrow to the right. How do you decide that? You look at the acid constant for H3O, which they say is 1, and the acid constant for hydrogen oxalate, which is 1.5 times 10 to the minus 4. Not all that low, but it's more than 1,000 times lower than H3O, so they're saying this reaction goes completely. The next step would be hydrogen oxalate. Reacts with H3O. And we get oxalic acid. Sorry, oxalic acid has one hydrogen on either end, so there we go. And there's water again. Now, oxalic acid, I have a bit of a problem with calling this a quantitative reaction. I would say this should be 2 arrows because the acid constant for oxalic acid is actually quite high. It's 0.056. This is not 1,000 times stronger than oxalic acid. It's more like less than 20 times stronger. So this reaction would have an equilibrium, and so I would say this reaction does not go to completion. We have one quantitative reaction and another one that's partial. That, I think, is the best way to say that one. This bugs me a little bit. I don't think we're going to pick on that. In fact, from what I've seen of the final, we do not bug you about that at all, but be aware that it's a quantitative reaction only if one acid is overwhelmingly stronger than the other one, and overwhelmingly is a fuzzy word. If there's an official cutoff, like 1,000 times stronger or 1,000,000 times stronger, I'm not sure what that cutoff is, so we can't be too rigid about what we call a quantitative reaction at this point. We haven't defined that well for you. But I hope you're comfortable with the concept of there being 2 reactions here, one with and 1 hydrogen getting transferred at each step. That's the big takeaway we want you to have. Okay, what else have they got for us? Hydrobromic acid. This is a top 6 acid, so it starts as HBr, but 1/1,000,000th of a second later, it's just H3O. So there goes our H3O, and we're adding that to sodium. Don't care about the sodium. Carbonate. So there's carbonate, and it meets H3O. Hello, I'm a very strong acid. Would you like a hydrogen? Why, yes, I would love a hydrogen. Now we get HCO3, and the H3O trades down to water. If we keep adding acid, our next step will be hydrogen carbonate meets more acid. Would you like another hydrogen? Well, okay. H2CO3, carbonic acid, and water again. So I've been obsessing a little bit about what kind of arrows to put here. I'm just going to stop doing that and put a single arrow. Let us understand that if these reactions have a large difference between the strengths of the 2 acids, then it'll go to completion. And if the difference is not large, in other words, if this acid is relatively strong, then there should be equilibrium arrows here, but I don't want to keep picking on that. It's the same issue every time. They're saying 2 quantitative reactions, meaning they believe it should be 2 regular arrows, so we'll just let it go with that. Acetic acid, also known as ethanoic acid, is CH3COOH. This is a carboxyl group, so this hydrogen can come off. This one's part of a methyl group, these will not. And we're adding this to sodium sulfate. Don't really care about the sodium, but sulfate is interesting because it's a base. The acetic acid could give away a hydrogen, which would give us CH3COO, ethanoate, and the sulfate ion can gain a hydrogen and become hydrogen sulfate ion. Now, if we keep doing that, if we have HSO4 and CH3COOH, in theory we could have a second reaction. I don't like how I switched the order here. I regret doing that. Actually, that's going to drive me crazy if I don't fix it, so excuse me. The order doesn't matter all that much, but I try to keep the order at least consistent. So in this case, it's the organic thing plus the sulfur thing. If we're consistent about that, it makes the reactions a little easier to read. So the reaction that could happen here is that acetic acid could give away a hydrogen, this could gain a hydrogen, and we'd get ethanoate again and H2SO4. However, I just want to note this reaction is extremely improbable because H2SO4 is a top 6 acid. It's one of the strongest known acids. On this side, we're saying that ethanoic acid is the one driving the reaction to the right. This thing's K is 1.8 times 10 to the minus 5, and sulfuric acid's K is more like 1,000. So this reaction, I'm going to put an arrow, but above it I'm going to put much less than 50%. That isn't required, but I feel like I should mention it, that if you take vinegar and put it with hydrogen sulfate and then sit back and wait for something to happen, you better get comfortable. This reaction is not going to go, because if it did, it would produce sulfuric acid, which would say, wait a minute, I'm one of the strongest acids there is. You take this hydrogen back, this equilibrium is going to be way over to the left, which is probably what they're referring to here when they say no quantitative reactions. This reaction is less than 50%, and actually, you know what? HSO4 is also stronger than acetic acid, so this reaction is also less than 50%. So we can write these reactions and say that the following is a theoretical possibility, but realistically, the equilibria are so far to the left that these reactions essentially don't happen, or they happen in such small numbers that they're not useful. And finally, nitric acid is HNO3, except when you put it in water, it quickly stops being HNO3 and becomes H3O, which is nice because it's acid, and nitrate, which we don't care about because it's one of the worst bases ever. And we're adding that to sodium, don't care, and carbonate, which is interesting because it can pick up hydrogens. So we have the characters we need to tell an acid-base story. We can say carbonate reacts with hydronium and produces hydrogen carbonate and water. And if we keep the acid coming, we can get hydrogen carbonate to react with yet more acid. We'll get carbonic acid and one last water.